Hey, good people, welcome back. In this video, we're going to learn about one-sided limits, specifically in relation to piecewise functions. And we're going to explore this three ways. We're going to look at some graphs, some tables, and some functions written in function notation. We're going to go through two examples of each of those, but before we do, here's the definition of a one-sided limit, the formal definition. The limit of function f of x as x approaches c from the right side is denoted by this little plus sign, this little superscript after the c. And what this means is that we're investigating how the function behaves as the x values approach this number c from the right side of c, meaning the values that are greater than c. And we have a similar notation for when we're investigating the left-hand limit, which is how the function behaves as the x values approach c from the left side. So this is the notation that we use to indicate whether we're investigating the function as it approaches c from the values greater than c, or as it approaches c from the values that are less than c. And this is indicated in this diagram over here. The limit from the right-handed limit, we use this little plus sign superscript, and the limit from the left-hand limit, we use a little minus sign superscript. Now, if the function approaches the same value from both the left-hand and right-hand limit, then we say that that limit exists as x approaches c. All right, let's look at an example where we just analyze a graph. Find the limits using the given graph. If a limit does not exist, indicate that it does not exist and explain why. So first, let's find the left-hand limit as x approaches -2. So we're now looking as x is getting close to -2, but we're looking from the left side of -2, the values that are less than -2. So we're right here. And we're strictly looking from the left side. As we get closer and closer to -2, it looks like the output value is staying the same. It's still equal to -1. So this function is equal to -1 as x approaches -2 from the left side. How does the function behave as x approaches -2 from the right side? So now we're coming along. We're approaching -2. We're at 0, -1, getting closer to -2. Looks like this function is getting close to the output value of -5 if you trace it back to the y-axis. So this is approaching -5 as we approach x is equal to -2 from the right side. So are these two left and right hand limits equal? No, they're not. So therefore, the limit as x approaches -2, the ordinary limit, does not exist. And for our reasoning, we have to explain why. We can just say that the left and right hand limits don't equal one another. The left and right hand limits are not the same, so therefore the limit does not exist. All right, and let's see another example, another graphical one. Find the limits using the given graph. If a limit does not exist, indicate that it does not exist and explain why. So this is there is some type of discontinuity here, this removable discontinuity. So this is a piecewise function. Let's first evaluate the left-hand limit as x approaches +4. As we get closer and closer to +4 from the left hand of +4, the y value is getting closer and closer to +4 if you trace this back to the y-axis. So the left-hand limit as x approaches +4 is equal to +4. And as we approach +4 from the right side, we're doing the right-hand limit now. We're going to get closer and closer to positive 4 on the right side of positive 4. And it looks like the output value is also approaching positive 4 on the y-axis. So because the left hand and right hand limits both approach the same number, then the limit as x approaches positive 4 is equal to, in this case, the number that these both are is also positive 4. So the limit does exist and it's equal to 4. Notice that this doesn't mean that the function's defined at 4 or that it equals 4 when x is equal to 4. In fact, you can see from the graph that when x is equal to 4, f of positive 4 is equal to negative 1, because this is actually defined at negative 1 if you trace it back to the y-axis there. That's not what this is asking us. This is asking us the limit as x approaches positive 4. So it's asking us how the function behaves, and it does have a limit as x approaches positive 4, and that limit is positive 4. All right, let's look at an example where we have to analyze a table of values. Find the limits using the given table. If a limit does not exist, indicate that it does not exist and explain why. All right, so we have to first calculate the left-hand limit as x approaches negative 1. So we're going to look as x gets closer and closer to negative 1 from the left side of negative 1, so from the values that are less than negative 1. So we're at negative 1.4, negative 1.3, negative 1.2, negative 1.1, negative 1.01. We're getting closer and closer to negative 1. And it looks like these output values are getting closer and closer to what number? 0.6, 0.7, 0.8, 0.9, 0.99. It looks like we're getting closer and closer to positive 1. All right, how does the function behave as x approaches negative 1 from the positive side, from the right side of negative 1? So now we're at negative 0.6, negative 0.7, negative 0.8, negative 0.9, negative 0.99. We're getting closer and closer to negative 1, this time approaching it from the values that are greater than negative 1. How do our output values behave? Negative 3.7, negative 3.65, negative 3.6, negative 3.55, negative 3.505. These numbers are getting closer and closer to negative 3.5. They're not approaching the same number. So the limit of the function f of x as x approaches negative 1 does not exist. And this is because the left and right hand limits don't agree. They're not the same. All right, and I went ahead and I graphed the function that behaved this way, and so you can see better that this doesn't have a limit as x approaches negative 1. Here's the function that I built this table from. It's a piecewise function. For values of x that are less than or equal to negative 1, it's defined as x plus 2. And for values of x that are strictly greater than negative 1, it's defined as negative x over 2 minus 4. And you can see that for anything less than negative 1 or equal to negative 1, it's defined by this linear function. And anything greater than negative 1, it's defined by this linear function. As we get closer and closer to negative 1, these two parts are at different parts of the graph. They're defined as different y values, so the limit does not exist. This is a non-removable discontinuity. This is a jump discontinuity. All right, let's look at another example where we're analyzing a table of values. We have to find the limit as x approaches negative 2 from the left side, then from the right side, and then determine if that limit exists. So as x approaches negative 2 from the left side of negative 2, negative 2.4, negative 2.3, negative 2.2, negative 2.1, negative 2.01, the y values are getting closer and closer. Well, they're getting closer and closer to 0. And as x approaches negative 2 from the right side of negative 2 from the values greater than negative 2, negative 1.6, negative 1.7, negative 1.8, negative 1.9, negative 1.99. We're getting closer and closer to negative 2. The y values, negative 0.2, negative 0.15, negative 0.1, negative 0.05, negative 0.005, the y values are getting closer and closer to 0. So in this case, since the left hand and right hand limits both approach the same number, we say that the limit of the function f of x as x approaches negative 2 does exist and it's equal to 0. And the function that I built this table off of, I'm going to show you a picture of it. Here it is. You can see that the limit does exist as x approaches negative 2 and it's equal to 0. As we get closer and closer to negative 2 from the left side, we're getting closer and closer to 0. As we get closer to negative 2 from the right side, we're getting closer and closer to 0. And if you were to evaluate the function when x is equal to negative 2, it equals 0. All right, now let's look at an example where we're asked to just analyze a piecewise function that's written in function notation. We have a piecewise function. We have to find a left hand, a right hand, and a regular limit. And let's interpret what this function is first. It says that the function f of x is defined as negative x over 2 minus 2 for all x values less than or equal to 2. For all x values that are greater than 2, the function is defined as negative x squared plus 1. So we have to interpret this piecewise function as different functions for different input values of x. Any input value that's less than or equal to 2, we're going to go with this definition. For any input value that's strictly greater than 2, we're going to go with this definition. So when we're doing our left-handed limit, we're actually approaching 2 from the left side, or the value's less than 2. This left-handed limit here, we're going to use the top definition because we're actually approaching from values less than 2, like 1.99, which is less than 2. So we're going to calculate this limit by plugging in, I don't know, maybe a number slightly less than 2, or we could even plug in 2 because a function is defined at 2. So let's just replace x with a number. And it looks like the function equals negative 3 when we replace x with 2. Now, we're going to evaluate the function when x approaches 2 from the right side now. Actually, from the left side, I just want to verify. Sometimes I like to approach it like 1.99, just get a little bit less than it. Yeah, it definitely approaches negative 3. All right, so now let's approach 2 from the right side. And we're going to have to use the other definition of the function, this yellow one, negative x squared plus 1. Negative x squared plus 1, I'm going to say from the right side of 2, 2.01. That's pretty close to 2, but slightly greater than 2. Negative 3.0401. If I get even closer to 2, maybe I'll put in 2.001. We can see that this is still getting closer and closer to negative 3. So this is approaching negative 3. And since they both approach the same number, we can say that the limit exists. And it approaches negative 3. All right, I went ahead and I graphed this one so you can see that it does definitely approach negative 3. Here's the graph. we see that as we get closer and closer to positive 2 from the left side, our output value is getting closer to negative 3. And as we get closer and closer to positive 2 from the right side, our output value is getting closer and closer to negative 3. So that limit exists and it's equal to negative 3. All right, let's do another one where we have to analyze a function just by looking at the algebraic definition. All right, so we have the function is defined as negative x minus 3 for all x values less than or equal to 3. And when x is strictly greater than 3, the function is defined as negative x squared plus 4x minus 3. So this has like two different definitions. It has, I guess, a linear part for all x values less than or equal to 3, and a quadratic part for all x values greater than 3. All right, we're going to evaluate the function as x gets closer to 3 from the left side of 3 by plugging that into this linear function here. So negative x minus 3. How does this behave as x approaches 3? Well, we get negative 3 minus 3, which is equal to negative 6. So the function, the left-hand limit of the function as x approaches 3 is equal to negative 6. All right, how does the function behave as x approaches 3 from the right side of 3? We're going to plug that into this function and see what we get. So as x approaches 3 from the right side of 3, we can try 3.1 if you want. How does this function behave? Negative 3.1 squared, or negative x squared. So we just plug in 3.1 for x. All right, I'm going to evaluate this and see what I get. This is approaching negative 0.21. I'm not really quite sure what that's approaching, so I'm going to make this even closer to 3. I'm going to add two more zeros, 3.001. 0.0, negative 0.002001. So this is actually getting closer and closer to 0. And I'm going to just plug in 3 there, verify that. As we get closer and closer to 3, this is approaching 0. So the left-hand limit and the right-hand limit don't match up. Therefore, what we say is that the limit does not exist because the left and right-hand limits don't agree. The limit does not exist. The ordinary limit as x approaches 3 does not exist because the left and right-hand limits don't agree. All right, and let's see the graph of this one. And you can see that this is it. This is correct. So as x approaches positive 3 from the left side of it, our y values, our output values, are getting closer and closer to negative 6. And as x approaches positive 3 from the left side of it, or from the right side of it, our y values are getting closer and closer to 0. So the two parts of the function don't line up perfectly. The limit does not exist. All right, so thank you for watching. The new assignment that you're going to get today is due June 2nd, which is a week from today. It's some questions exactly like these. You're asked to evaluate some limits, some left side and right side limits, and some ordinary limits. If they approach the same number, then the limit exists. You have to do some graphical problems, some tables, some problems where you have to evaluate the piecewise function just by plugging it in algebraically. And this is the last assignment that I'm collecting. So this final assignment is due on June 2nd. And we will have one more lesson on June 2nd, but that will not have an assignment that goes along with it. So we'll have a lesson next week on June 2nd. The topic of that lesson will be on the continuity of functions or reasons for discontinuity. And there will be no assignment that accompanies that lesson. Thank you for watching again, and I look forward to seeing you in our video meeting.